Today, we are solving the problem of the sequence. The problems are all from the Real AMC8, the math contest. Number 1, this is 1998 AMC8 problem 22. Terry produces a sequence of positive integers by following 3 rules. She starts with a positive integer, then applies appropriate rule to the result and continues in this fashion. Rule 1. If the integer is less than 10, multiply it by 9. Rule 2. If the integer is even and greater than 9, divide it by 2. Rule 3. If the integer is odd and greater than 9, subtract 5 from it. A sample sequence 23, 18, 9, 81, 76. Find the 98th term of the sequence that begins 98, 49. Now, we start the 98, this sequence, and because it's the even and greater than 9, so divided by 2, that will be 49. 49 is the odd and greater than 9, subtract 5 from it, will be the 44. 44 even greater than 9 divided by 2, we get 22. 22 still divided by 2, that's the 11. 11 greater than 9 and odd, subtract 5, that will be 6. After the 6 is the less than 10, multiply it by 9, that's the 54. 54, that's the even, divide by 2, that's the 27. 27, then subtract 5, that will be 22. Look at, now we continue. So from the 22, 11, 6, 54, 27. After the 3 terms will be cycling from the 22, 11, 6, 54, 27. That's the 98. They ask 98th term. We minus first the 3 terms equal to the 95. 95, because the 5 number repeating, we use the 95 divided by 5. That's the remainder. We will see the remainder. Remainder is the 0. That means it's the last number of the 20 of this cycling. That's the 27. Actually, usually we do is the 22, 11, 6, 54, and 27. When the 5 number cycling, repeating, if the remainder is the 1, that means that's the 22. Remainder, that's the 2, will be 11. Remainder 3, 6. Remainder 4, that's the 54. If remainder 0 divisible by 5, that number is the 27. So remainder from 1, 2, 3, 4, 5, that's 5 number, cycling number. So the number 1, the answer is the D, 27. Number 2, this is the 2000 AMC10 problem 6. The Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21 start with 2 ones, and each term afterwards is the sum of its 2 predecessors. Which of the 10 digits is last to appear in the units position of a number in Fibonacci sequence? Now look at this Fibonacci sequence. 1, 1, and the sum of 2, 1, that's the 2, 3. Continue on this one, that will be the 5, 8, and then 5 plus 8 is the 13. We just write down the ones digit. And 8 plus 3, that's the 11. I put the 1. 3 plus 1, that's the 4. 1 plus 4, that's the 5. 4 plus 5, that's the 9. 5 plus 9, that's the 4. 4 plus 9, that's the 3. 3 plus 4, that's the 7. 3 plus 7, that's 0. 7 plus 0 is the 7. And 0 plus 7 is the 7. 7 plus 7 is the 4. 4 plus 7, that's the 1. 1 plus 4, that's the 5. 5 plus 1, that's the 6. Now, the last number is the 6. Look at, we have the 1, 2, 3, 4, 5, and 6, and we have the 7, 8, 9, and 0. So the last number of the 10 digit, that's the 6. So the answer is C. So we don't worry about the 10th digit, 100th digit. We just look at the ones digit. So every calculation, I just keep the ones digit. That's our target. The answer is C. Number 3, this is 2002 AMC 10B problem 23. Let AK be a sequence of integer such that A1 equals 1 and AM plus N equal to AM plus AN plus MN for all positive integer M and N. Then A12 is, so first we know that's the A1 equals 1 given. A2 we write as the A1 plus 1, that will be the A1 plus A1 plus 1 times 1, because the formula they gave us is the AM plus N equal to AM plus the AN plus MN. So A1 is the 1, A1 plus the A1, that's the 1 plus 1 plus 1. So A2 equals 3. And the A3 equal to A1 plus 2, they equal to A1 plus A2 plus 1 times 2 equal to 6. Now next one, have the A3. Now we can do the A6. A6 equal to the A3 plus the 3 equals A3 plus the A3 plus the 3 times 3, that's the M times N. They equal to 21. With the A6, we can do A12 equal to A6 plus 6 equal to A6 plus A6 plus 6 times 6. A6 is the 21. So 21 plus 21 plus 36, that's the 78. So the answer is the D, 78. Number 4, this is 2004 AMC 10A. Problem 18. A sequence of 3 real numbers forms an arithmetic progression with a first term of 9. If 2 is added to the second term and 20 is added to the third term, the resulting numbers form a geometric progression. What is the smallest possible value for the third term of the geometric progression? So we know that the sequence, that's the arithmetic sequence, with the first term, that's the 9. So have the common difference. Second term will be 9 plus D. Last term will be the 9 plus the 2D. The general term is the AN equals the first term plus the n minus 1 times common difference. So first term is the 9, second term 9 plus D. The last term is the 9 plus the 2D. Then the 2 added to the second term. First term is the same. The second term, the 9 plus D plus 2, will be the 11 plus D. And the third term add to the 20 will be the 29 plus the 2D. And the second sequence is the geometric sequence. We know geometric sequence have the common ratio, so we use the 11 plus the D divided by 9, that's the ratio. They equal the 29 plus the 2D divided the 11 plus the D. That's the common ratio, is the second term over first term, or the third term over second term. That's the two adjacent term, the ratio is the same. Now cross multiplying 11 plus D bracket square equal to 9 times 29 plus the 2D, and expand the square of the sum. That's the first term will be 121 plus the 2 times 11, 22D plus D square equal to 9 times the 29, that is 261 plus the 18D. And then we simplify the equation, D square plus the 22D minus 18D, that will be the 4D. And then 261 move to this side, that will be the negative. So 121 minus 261, that's the negative 140 equals 0. So now we do solve the quadratic. D minus 10 and D minus and D plus 14 equal to 0. And then the D equal to 10, and also D equal to negative the 14. The question asks about what is the smallest possible value of the third term of the geometric progression. So when D equals the 14, plug in here 29 minus 2 times the 14, that's the 28, so equal to 1. The answer is the A. Number 5. This is 2004 AMC 10B problem 19. In the sequence 2001, 2002, 2003, each term after the third is found by subtracting the previous term from the sum of the two terms that precede that term. For example, the fourth term is 2001 plus 2002 minus 2003. It's the 2000. What is the 2004th term in this sequence? Now let's solve this problem. So we write the sequence. That's the 2001 first term, second 2002, third 2003. Next one is the 2000, already the calculate. And the next term will be the 2002 plus 2003 minus 2000. That is 2005. And the next term will be the 2003 plus the 2000 minus 2005. That is the 1998. So next term is the 1998. Hopefully we can find the pattern. So look at the first term, 2001, third term, 2003, 2005. It's arithmetic sequence. Common difference is the 2. And the second term, fourth term, and the sixth term is also arithmetic sequence, but the common difference is negative 2. Now, look at the question. They ask the 2004th term in this sequence. 2004th term, that's the even term. So it goes the sequence like this. 2002, 2000, 1998. The 2004th term, that's for the even term. That will be the 1002. So the 1002th term, so we use the A1002. They equal to first term. That's the 2002 plus the n, that's the 1002 minus 1 times common difference, negative 2. We use the general term an equals a1 plus the n minus 1 times common difference. So that's the 2002. That's the 1002 minus 1. That's the 1001 times negative 2 will be the negative 2002. So the result is the 0. So the answer is the C, 0.